This is Module K, Siemens Timers and Counters. So we'll start our slideshow here and see where we're at. So Siemens Timers and Counters. Once again, the activities would be that you would have got the PowerPoint, and then that's what you're looking at here. You can click on the link to watch the lecture video. You'll there's one stop here where we got to stop and watch another timer video. It's pretty important that you pay close attention to that. There's a little bit of a lecture worksheet, and then you're going to complete a crosstalk activity, and then you'll turn that in. So here's our video lecture outcomes. We're going to describe how the asynchronous scan of the Siemens timers provides different functionality than that of those of an RS Logix. Asynchronous scan, it gets to be critical in these third generation PLCs, and we'll go over that. Describe the purpose of interlocks between two controllers. Describe four functions and relays. And here we go on the Module J review. So on the Model J, we did a lot of scheduling. So I just wanted to take a look at the Flex scheduling. The Flex is the big automated system down in the Center for Manufacturing Excellence. And I just wanted to show you that if you came into the Flex, here's the Control Logix program for a little bit different than Siemens, but you have the tree over here. And here is our main task. So this is what is the main task, is what is continuously scheduled. If I go into the main here is continuously scheduled, and this main program here is continuously scheduled. So it's gonna run this first. So if I look into this main, you're gonna see that there's some stuff up here, some housekeeping, but really what's in this main is there's a lot of unconditional call subroutines. So this calls this subroutine, this calls this subroutine, calls this subroutine, subroutine. There's 12 or 14 unconditional calls of subroutines in here. Here's a conditional call of a subroutine right here. So this one, there is a conditional, but that's all you got in the main. And then these are the subroutines right here that main is calling, okay? And so it runs this main program here, and then what it's going to do is it's going to run this main program. And once again, this main program is just going to be calling all different types of pretty much unconditional calls of subroutines, okay? So that's the way the scheduling of this looks, and you start thinking, well, you know, what is going on? Let's take a look at the robot here. No, same thing. Let's take a look at the conveyor. I'm sorry. So you start thinking, well, where's the inputs and the outputs? You know, all I'm seeing is scheduling and subroutines. Well, that's right. It's hard to find your outputs if you don't understand what's going on with scheduling here. So if we go back here, we're running our main, so it runs this main, and if this main calls these subs, it runs it. Then it runs this main continuously, and if these get called, it runs those. If not, it doesn't. Calls the main here, calls the main here, calls the main here. So it runs through these scheduling, finally gets down here to conveyor, runs the main here, and if we look at the outputs here, maybe we got something. Oh, here we go, finally. Here's a data bit 4 on the output module, data bit 5, data bit 8. So here's finally, you're starting to see some outputs here that are getting turned off and on, depending on if this main, looks like we're looking for jump to subroutine outputs. It is a unconditional call of this output sub. So now this logic is going to get analyzed, and if some of this stuff is true, well, then we'll start getting the conveyor turned on. So that's an example of what's going on the scheduling at the Flex. And as you can see, it's pretty complicated, and that's why we went over scheduling, to be sure that you understood, you know, why things are running and why things are not running. So let me see if I can close this right there, and then I can come back to this right here, and we'll keep going here. So we talked about the project tree where there was continuous projects. Alan Bradley, I just showed you, had continuous tasks, programs, and routines. The Siemens just does programs and routines. And we talked about what was continuous and what was periodic. And also we talked about how the routines, these are what gets scheduled or called out of the programs, and these are what contains the ladder logic, or it contains the FBD. These contain the logic or the routines, but they don't run unless they're called. Okay. So one task can be executed at a time. This is on Allen Bradley. We talked about programs and tasks having priorities. Higher priorities interrupt lower priorities. Usually the continuous tasks are low priority, and any kind of intermittent stops that from running, and it would run the higher priority tasks. Okay. Programs are scanned in order on the tree. That's what I just showed you. So on that Allen Bradley, it was running, you know, all those other programs first before it made it all the way down to the conveyor to even then start seeing if anything was scheduled to run that. So it runs them in orders because they're scanned continuously. And in those programs, those are scheduling the routines. And inside the routines, that's where our ladder logic is. So routines, you have a main routine that's scanned continuously, and there can be more than one routine that's scanned continuously. In the main routine, it schedules the subroutines. So whether they're unconditionally or conditionally scheduled, and that's where the subroutines contain all the ladder logic or FBD or ST, however you want to program them. Large continuous routines are broken into smaller routines in order to modularize it and organize it. We talked about continuous versus periodic, and we did a hardware interrupt, right? So tasks are scheduled by the PLC hardware configuration. We had an input calling an hardware interrupt, and that overrode everything and then jumped back to the main. They can be event-driven or time-driven. We had a event-driven by pushing a push button. Continuous tasks always execute, and continuous tasks are interrupted by these periodic tasks. Scheduling on the main OB, it's always scheduled, and it's a continuous task. And then we ran our subroutines FC and FB out of the main, and we could conditionally or unconditionally schedule the FCs and FBs. A scheduling task or routine will provide retentive outcomes once it is unscheduled. So this is what we learned. So let's say we turned on a light in a subroutine. For example, we turned that light on, and then we unscheduled that routine, that FB or FC. Well, the light stays on unless you turn it off in another subroutine, or unless you turn it off in the main. So you got to be careful that when you jump out of a routine, the items that are on in the routine stay on. Therefore, routines are often unconditionally scheduled. And if you do conditionally schedule them, you're going to need some way to kind of reset the output back in the main routine, or else it's going to stay on. Retentive scheduling. So we talked about the retentive nature of a startup OB. So we ran a startup OB where we turned on all the lights, and then as soon as that startup OB was done, well, then the lights stayed on. We had to turn them off. So in event-driven OB, you can get the same thing. That if you turn the lights on and you jump back, they'll stay on. You got to turn them off. And then we had a reset push button or reset function block, and the purpose of that was to turn those on. So if these were turning the lights on, we use the reset to turn them off, and we will review the lab. So I just want to be sure you're aware. The lab may or may not provide practical applications. It was just meant to demonstrate desired and accidental incomes due to scheduling. Okay, so if you really looked at the lab and you were trying to figure out what was going on while you were programming the lab, that's great. Trying to say, hey, wow, that's on. This should be off. I got to turn this on. I got to turn that off. And you were looking at the logic repeatedly and frequently. That's what this was about. Okay, you probably don't want to program this way. You know, you can do a lot of crazy things, but it says it's a good or bad idea to use the outputs more than once in the different subroutines. What we did in this lab, probably not a good idea, because we had some very complicated logic here, and it becomes difficult to troubleshoot. So it's better if you use bits. You know, you need to turn the output on and off multiple times. You can have an OR and use memory bits and put them in OR to do it. That would probably be a cleaner way. So it is possible to use outputs more than once, as long as the logic contained outputs are not scheduled to be scanned at the same time. And we did a lot of that in this lab, but it becomes a troubleshooting nightmare to try and figure out, well, where I've used the output 3 times, in which one of the routines is currently being scanned to turn that on or off, and also what was the retentive nature of that output when we unscheduled the sub. So the moral of the story is you probably don't want to use an output more than once. You can if you really need to, but you got to be a scheduling wizard, and you can make just about anything happen. Okay. Let's just run the lab real quick. So we did the OB100. So the OB100, it just ran one time. Every time you turn the CPU on or off, it automatically calls the 100. It schedules it. So on, and then after one scan, it jumps out of this sub and back to the main. Well, the lights were turned on, it jumped out of the sub, so they stayed on, because in the main routine, there wasn't anything that was turning them off. So that's that retentive nature that I'm talking about. If you turn something on in a subroutine, and then you unschedule the sub, those items are going to stay on. So then we had the system reset. Well, then what we did, well, the lights were on, so we pushed the button. And so when we pushed the reset button, what that did is it scheduled the system reset. And the system reset called this sub right here. This is the ladder logic in that sub. And so remember, this ladder logic doesn't execute unless we push the button and call it or schedule it. So then this runs. So because this is never true, well, then this is off, and the lights go back off. So that's the way that worked. The system checked one scan, turned them on, pushing the reset, scheduled the system reset. While we were holding it, which happened to turn them off, we let the button off. These return to the state which off. So once we unschedule it, they stay off. Ejection seat. This was conditionally scheduled. So once again, we had to push this button to cause the ejection seat subroutine to run. And this was the logic in the subroutine. Basically, we just turned the light on and we used a set bit to turn it on. We probably didn't even need the set bit, because if we push the button and schedule ejection seat, this turns on, and then when we let go of the button, ejection seat is no longer running, and so the last status of Q0.0 ejection seat armed would have stayed on, and it would have been on, it would have been retentive, but we used a set bit just to be sure. Autopilot. So the autopilot was conditionally scheduled, and what we did here is we used a toggle so that it's the same toggle, or excuse me, it was related to the status of the autopilot. So if the autopilot is on or off, you can only have one of these things occurring, either the autopilot or the manual. Okay, so we looked in the autopilot as armed. We were trying to get the autopilot engaged, and once again, input 0.6 was a toggle. You could either you can't have, the way the toggle works, both of these can't be scheduled at the same time. So you're either running auto or manual. So we jump in the autopilot. We have the autopilot light engaged. We'll either turn it on, and then this one right here is the manual control, which, because it's never true, it will be off. So even if we did turn autopilot on and we had the light on, and then we schedule the manual, because that's never true, it would turn it off. So that's how that toggle switch was working. We put the reset bit in here so that it automatically didn't schedule the manual, depending on the switch status. Because if this switch was true and we didn't have the reset bit, it was automatically going to do the manual, and it was automatically going to turn the light off. And what happened was, when we cycled the lights, only 4 of them came on, because the 5th one came on, but it was only for one scan, and we couldn't see it because immediately manual ran, which turned it off. We put the reset bit in there, and then we said don't run the manual until we've pushed the button and turned all the 5 lights off. The fuel check was unconditionally scheduled, so it automatically ran this, and so the system check bit was going to give us, because it was an OR, was going to give us the low fuel light, and then we needed the sensors here. And we brought the sensors on, we were going to get that low fuel light. That was just an example of unconditionally scheduled. Here was a jamming radar, which was unconditionally scheduled as well. And in here we had just an and/or situation going on here to try to get the jamming radar to come on. And then the missile system was another unconditionally scheduled, and this just had a big fancy and/or with a lot of knots right here in order to get the missile system armed. And so the purpose of this was just to leave that light on when we push the system check. Here was, we had a couple things going. Here was a push button PB system check. So this was not a hardware call, but the hardware call was working similar to the logic right here. This was not a hardware call. Basically, somebody added another push button that said test lights. So we were either doing the check or the reset, okay? Because it was going to get called. Either the test was going to get called or not get called. This was either going to be true or not. So when we push the button, it was either going to turn all the lights on momentarily, and then when we let the button go, it was going to this was going to open, it was going to turn them all off. So this was a way to check all the lights within the program. The difference here is that if we had a retentive light, such as the ejection seat armed, it would go on and then it would go all the way off. So we would have to rearm the ejection seat if we did it this way, okay? Now with the hardware interrupt, we are able to call a similar sub to this with the hardware interrupt rising, and then this for the hardware interrupt falling. And so what that did was allowed us to check the lights, because it would run the hardware interrupt one time, and then it would return these to the state. And the way that this worked is it actually didn't affect the ejection seat armed light. You had homework and a quiz. Be sure you understand that. We're going to take a look at the homework problem for scheduling of the robot. So the robot homework had an auto, a manual, and a maintenance toggle. So because this is a 3 selection toggle, it had 1, 2, or 3 different inputs right there. And then there was a prox, and then there was a push button, and there was a crosstalk to the robot. So we had all these inputs, then we were going to talk to the robot. And then a never true bit, I made an M bit. So what did this look like? Well, we had 3 subroutines. We were going to run automatic, manual, or maintenance. And because this mode could only be one or the other, it would be either auto, manual, or maintenance. If you wanted to really do overkill, you could have put a close contact here, 2 close contacts, and interlocked them with this one, and 2 close contacts, and interlocked them with these ones, and 2 close contacts, and interlocked it with these ones, so that you're sure that you're only calling this one, or this one, or this one. If for some reason this switch malfunctioned, okay? So, but either automatic, manual, or maintenance are going to run. Can't run more than one. What do they look like? Well, let's take a look at the maintenance one right here. So we're calling the maintenance. Here's where I got the interlock. So the maintenance switch has been selected in order to call this subroutine in the first place, but the maintenance switch is also opening this, causing this to be false. This is never true, so that is false, and the robot crosstalk is therefore always going to be false, okay? So in the maintenance network, we have the robot crosstalk. The prox signals cross. So if we schedule the automatic, we just had a prox doing some type of a pulse timer or something to the robot crosstalk. And the other one was, if this was the manual was selected, well then we needed the manual, we needed the prox, and we needed a manual person. The person manually had to push a button, so prox and that to cause the robot to crosstalk. Okay, so here we go again. We've used this output 1, 2, 3 times. Is that a good idea? Well, it works, but maybe that's not the best idea. Maybe it would have been better if this would have been M1. I'm sorry, we've already used the first M0.0. This could be M0.1, M0.2, and M0.3. And maybe we have another subroutine, or even in the main, where we have M0.1 or M0.2 or M0.3 call the robot crosstalk. That'd be a little bit cleaner. That way we're just looking for the status of the M's, and we could return this to its own subroutine, or we could return this to the main, and it'd be easier to troubleshoot that Q 0.0. So we're talking about Siemens timers and counters. So the timer types for Siemens are TON and TOF. This is just like the SICK 500, where we had on delay timers and we had off delay timers. Okay, what this adds is a pulse timer. So a TP is often used for a crosstalk interlock and other timing applications. And you'll see that a TP kind of acts like a timer timing. Like once you make the TP true, even if it's only for a second, you can push the button and let up. It's going to go ahead and time out for half a second or a second, whatever it's set to. Whereas this TON, you have to keep the rung true the whole time in order for it to time. And when you let it go, it resets. So TONs, TOFs, and there's retentive versions of this. And then the pulse timer. So how is it added? Well, you can add it from the toolbars, or you can just drag in the command here with the question marks in it, and then you double click the question marks, and then you can pick TON, TOF, you know, for the counters. That's the same way. Add the counter up, counter down. So this is a quick way to add it. Okay. Here's an example of the timer. So if you clicked on that, you would see TON, and you'd see the function. It looked like kind of FB format. Looks like coming in as a block. All right. And so don't add it as a coil. You could add a TON, and there's a version of that that adds as a coil. Well, the problem is there, it needs a dB. So then you would have to add a dB in addition to that. If you put it in here as a block right here, what happens is it creates a dB for this block to keep track of the time. Okay, so in this case here, it's coming in. We programmed it in ladder, and it shows that this is the enable right here, and shows that it's being scheduled, or you could put a contact here to turn it on. Okay, if you put it in as an FBD programming language, it comes in. It looks almost exactly the same, except for the input here. It wants you could make it conditional. You could put an input here to cause this to go. Okay, so it's going to look like either one of these right here. You're probably going to be programming in ladder logic, so you're going to have an input turning on a timer, and that's what I'm going to be showing you. But what you don't want to do is put these timers in as a coil. Put them in is this function block or FBD look here as a block, and that's the way that they went in when we programmed Allen Bradley's. They came in as a block. So we've got different data types here. So here's my IN. So this is just whether it's on or off. So that's Boolean. It's either true or false Boolean. Okay. So this is my time. This is how long it's timing for. So this is going to be a word. So this is coming in as a word. And if you put in like 4S, it'll take 4 seconds, or 2S, 2 seconds. So that's how long I'm going to be timing for. And same time here, ET. This is going to return a value of how long it's timing. So it's going to be in seconds, so that is going to be a word, because it's not off and on. It's going to have some actual value. And then Q corresponds to a Boolean. Is it done, or is it on or off? Is it done timing, or is it not timing? So those are the data types associated with these timers. So IN makes it true. That's kind of like the EN bit. So if it's true, you can use the IN. It's enabled. It's on, instantaneous. PT is the preset time in milliseconds. So you can type 2000 and it would give you 2 seconds, or you could just type 2S and it would give you 2 seconds. So either 2000 or 2S gives you 2 seconds. ET is accumulated time. It's kind of like the ACC bit, accumulation bit, .ACC. And Q is whether it's done or not, and that's just like the done bit, the .DN bit on the Allen Bradley. So they're very similar, and the lab runs you through showing how these work. Here's something that's very important. So I'm just going to read this. You can have multiple updates of a timer in the same scan. Okay, consider what that means. The timer can be updated multiple times in the same scan. So let's say I'm reading this, and I'm reading this, and I'm reading this, and I'm reading this, and let's say the timer is here. It could get updated. But then as I read this and read this and read this, the timer up here could get updated again in the same scan. As I'm scanning here and reading this and reading this, it could get updated again in the same scan. So it doesn't go all the way through the scan before it updates the timer. It could get updated a bunch of times, and that is the asynchronous nature of this timer. That the timer scan is out of sync with the I/O or the ladder, with the ladder scan, and this has serious implications. Okay, It says the timer is updated each time the instruction is executed, and each time the queue or elapsed member is looked into, is used as a parameter. Okay, so if you use the, for example, you're looking for the equivalent to the ACC. We were looking for the accumulation, right? Or if you look for the queue to see if it's done. If you look at the timer, let's say the timer's here in the middle, that's fine. You look at it, or if you or down here in ladders, you're reading farther down and you look at the queue of the timer that's up here. When you look into that timer, no matter where it's at on the rung, the timer is updated, which means that depending on how you programmed it, it could be reset. So that timer could be reset 3 times in the middle of a scan, which means that it's certainly never going to time out, because let's say you had a 1-second timer. That timer is never going to get to a second because the scan is only a few milliseconds. So it's an advantage if you want the latest time data. It's immediate read of the timer at any time, no matter where you're at, working down the structure or the ladder. However, you desire to have a consistent values throughout a program scan, then place your timer prior to all other instructions that need these values. So that could work, okay? Use tags from the queue in the ET. So from the done bit and the ACC, put tags on the end of them. Don't, instead of using like .q and .et, kind of like when we were using the .dn and the .acc, just put tags on there, okay? And then that will take care of that. And so another thing is that if you separate the timers, let's say you have a timer and then you have ladder logic and you have another timer and ladder logic and a timer, and this ladder logic is accessing the different timers at different times as it scans and reads through, well then these timers are going to be reset in the program. And if we use counters and timers together, they're going to be resetting. Use tags instead. This cascading timer example video is a little bit long. I want you to watch it. Be sure you fully understand how this cascading timer works. So just to recap, here's the first one. I like this because the light's on its own rung. Do that. Put the light on its own rung and then turn something off or on. This worked. If you really want to mess this up, if you took this piece of ladder logic right here and you moved it down here between the timers, okay, now you're going to start getting in trouble because of the way that these timers read and the way that we access them. You might get a situation where one of these timers kind of resets prematurely because we're looking into the status of the .q bit, okay? So the .q bit, I told you, probably not the best way to go here by picking the Q off. This worked because the timers were cascaded right next to each other. Same thing if you put this in the middle here and you put some other counters and stuff in here that are looking at the timers, and it's not going to work. It'll reset, okay? Here was the next one. This worked as well. I recommended not, this is better because we're not using the Q bit to turn the light on, and we're using an M bit here to signal it's done. But I don't like this because the light is not on its own rung, and therefore if you want to turn it off, then you just, putting a contact here may or may not do it, because now you've got all these conditions here, this timer and the timer and then other bits to determine the light's on. Put the light on its own rung. Okay, so that's a solution there. This was a really good solution where we move the light on its own rung, and we're using bits here. Instead of using the .q, we're using bits that are tied to the Q. And then this works quite a bit better. This is probably the best practice. And this was probably not a good idea. We showed that this works. But as soon as you add something else in here, like you start using counters and stuff that are looking into these timers, that start looking into the accumulation here, well then that's going to cause these to automatically reset because of the asynchronous scan once you start using counters looking at these, or you start looking compares or something compared to this. So this is cool the way that this works. This is true, which starts a timer, light comes on, and then it starts this timer, done, reset. But this could be a disaster. And if we just did the Q here, and put the Q here, right away I think that this would fall apart instead of using this M bit. Okay, probably not a good idea. Siemens counters. Siemens counters go in very similar to the timers. You put in the box and you pick a CTU, be sure it goes in a box. R is the reset, it's Boolean, true or false. PV is the preset, this is what you want the counter to, 5, 10, 15, 20, and that's going in as a word because it's not true or false. CV is the count value, and Q is the done bit. Counters behave like timers. You can get an instantaneous read on them, so I recommend using bits on here instead of pulling the dot Qs and the dot CVs and everything right off of here. Better to use some type of bits. So here's the crosstalk activity I'd like you to do. For this, you're going to need a SLC 500 controller and a Siemens controller. And so what you want to do is you want to have the SLC 500 energized, push button energize the light on the SLC 500, and then that is going to turn on the light on the second controller. And then a PB on the second controller turns off both lights. So this is a little bit of in-class activity that you will work up. There is a quiz, and then there is a lab this week.